Спасибо большое. Так что значит, я прочитаю на английском, да? Okay. So, title of my presentation is Chemistry at the Service of Biology and Medicine. And I'm actually a chemist, organic chemist, and I'm specialized in chemistry of biophosphorus. And phosphorus, as you know, plays an essential role in many life molecules. It's an essential component in DNA and ATP and many other important compounds in nature. And in addition, it is found in many important drugs. I'm going to talk today about two recent examples of attempting to apply chemistry to medicine from my own laboratory. The first has to do with the problem of drug imaging, trying to find out where does a drug go and how does it work. And the second is a new approach to take a drug, modify it into the form of a prodrug, in so doing, improve its pharmacological properties in some advantageous way. So let's start with the problem of bisphosphonate drugs. These drugs are centered on the entire class of bone diseases. In particular, resorptive bone diseases. In resorptive bone disease, the bone essentially develops pores, becomes thin and brittle, and ultimately becomes prone to breakage. This is a disease that particularly affects older people and is prominent in women, in whom it begins in middle age, around the age of 40 to 50, and then it becomes progressively worse, shown by this progression of disability due to gradually decreasing bone function. This is a very serious condition and affects millions of people in the United States alone. There is a class of drugs developed about 25 years ago to treat, or at least to help to prevent the progression of bone disease. This is the structure of the general class of these drugs called bisphosphonates. In a bisphosphonate, you take the structure of pyrophosphate, as you might find it in bone, and you replace the bridging oxygen by a carbon atom. And this has two results. One is this is now a stable compound, natural phosphoric acid anhydrides, such as pyrophosphate, are not stable in aqueous solution. And secondly, because carbon is tetravalent, you have now two new places on the carbon atom to modify it. You can add substituents. The bisphosphonates act against resorptive bone diseases because of two separate and distinct properties. First of all, they have a great affinity for bone. And so if you take one of these drugs, most of it is excreted, but the rest goes into your skeleton, and it stays there. And this is because bone, of course, is itself a phosphate mineral. It's a calcium phosphate mineral, and so the pyrophosphate mimic bisphosphonate easily binds to the calcium on the surface of bone mineral. But there is a second effect of these compounds which makes them drugs, and that is that they target a specific enzyme in the mevalonic pathway, which is called farnesyl diphosphate synthase. What this enzyme does is it builds a kind of hydrocarbon, which is called a terpenoid, or terpene, and then it attaches it to small proteins which then become very hydrophobic, so they relocate within the cell into the cell membrane, and there they have a signaling function. And so if you block the action of this enzyme, you block this process of synthesis of the alkyl chain, which modifies these enzymes. Therefore, they can't relocate to the membrane, and this damages the cell in its signaling function. And why would you want to damage the cell in its signaling function? Because you are targeting not just any cell, but the cells responsible for the disease of bone resorption. These are cells that dissolve the bone. Why do we have such cells in the first place? They're completely natural. If, for example, you have a fracture in your wrist, you have an uneven and irregular surface of the bone that has to be cleaned up. And so these cells will dissolve those irregularities, and then related cells called osteoblasts reknit the bone material together, and you have a good wrist bone again. The problem in the disease is that these dissolving cells, the osteoclasts, become gradually out of balance with the building cells, the osteoblasts, and begin literally to dissolve the skeleton and to thin skeletal bones. So these drugs are designed to stop that process. Here's some examples of these drugs, and I want to focus on just a couple of these. One is called risedronate, and the other is called zoledronate. Both of these drugs enjoy a $1 billion per year market in the United States alone today. So they're used by a huge population. Recently, these drugs have found a second application. And it was found that if you apply these drugs intravenously in very high doses, they can be effective against bone cancer. In particular, they alleviate bone pain. And there are many observations supporting the idea they actually have an anti-tumor effect, tumor in the bone. And therefore, they have a potential great importance for treating cancer, but this importance is threatened by a side effect. The side effect is called ONJ, which stands for osteonecrosis of the jaw. This is a very peculiar side effect. The patients, cancer patients who are taking these drugs, go to the dentist. They're usually a bit older, so they have dental problems. The dentist removes a tooth. And in the tissue near the extracted tooth socket, this kind of fissure opens up, which does not heal, and it exposes the jawbone. The jawbone becomes necrotic and is expelled. And the result is essentially a hole forms in the jaw. So this is a very serious side effect. It seems to be associated with the use of bisphosphonate drugs. And so currently in the United States, if you go to the dentist, you get a paper, a little paper which you sign. You say, if you are taking bisphosphonates, you understand you're at risk. What that really means is, dentist, I promise not to take you to court and sue you if I get this side effect. On the other hand, the cancer doctors, the oncologists like this drug, and so there's a lot of tension between the dental community and the oncological community. So the basic problem is, for some reason, although the drugs are very popular and have been around for years, not much is known about how they really work, where they really go. Are they really in the jawbone, for example, in the first place? So to address this problem, we came up with some chemistry, which we call magic linker chemistry. We take a very simple compound. This is an epoxide with a single carbon attached to it, and attached to that is either an amino function or a chloride function. The amino function is protected with a group called a Bach group. And we use this as a linker to connect the drug to a fluorescent label, such as a fluorescent dye. And that fluorescent dye can be any among the commercially available fluorescent dyes, which have different useful properties, and that includes infrared dyes, which permit you to see very deeply into the tissue with the fluorescent signal. We call it the magic linker because of its very interesting chemistry, which I'll be brief about. So we take our magic linking compound, and here is one of the two drugs I was talking about, residronate. You notice residronate has this ring, a six-membered ring with nitrogen in it. It's called a pyridine ring for the non-chemists. And our task is to attach the fluorescent label without too much modifying the drug itself, then it's no longer the drug. The magic linker reacts with the drug without anything needed to be added to cause that reaction to be achieved in water with a little alcohol close to room temperature, and it reacts only with the side chain group, but not with the phosphonic acid group, which could cause the drug no longer to bind to bone. Once this linker has been attached, we can take off the Bach group, have a free amine, and with the free amine group, we can attach dyes. So once we had made a few of these magically linked bisphosphonate drugs connected with fluorescent dyes, we gave them to biologists. And biologists immediately got very interesting results with our compounds. For example, here in the panel D, what they've done is they've taken a bone mineral, dentine, they have exposed it to the labeled drug, and this has made the surface of the mineral fluorescent, as you can see, the green fluorescence. And they had captured in the microscope an osteoclastic cell. You can see the osteoclastic cell is already starting to dig a pit in this bone mineral, dissolving the bone. And as it does so, you can see that the drug is actually entering into the osteoclast. So in a simple picture, in a simple experiment, we show indeed that a part of the mechanism of these drugs is simply that the osteoclastic cell receives the drug that impairs its function simply by its normal activity on the surface of the bone. Here is a better image of the second drug I mentioned, also now magically linked to a fluorescent dye. And our colleagues at UCLA in Los Angeles used this fluorescent compound to study whether or not the drug distributes into the jaw as well as into other parts of the skeleton. So this can be seen qualitatively very easily. This is a fibia of the rat. You can see that there is drug uniformly through this bone. But more importantly for us, here's the jaw, here's the tooth of the rat. And you can see that there's a lot of drug in the jaws. So the idea that these compounds are associated with the ONJ side effect is certainly supported by this result. Also, you can see that the way the drug deposits in the jawbone is very uneven, has areas of high concentration, which may be suspect. An advantage of these compounds is that they still work as drugs. So here is the effect of treating with the labeled drug. This is a section of bone. You can see there's a lot of bone left in the middle, and without the drug, this is in a special vitamin D deficient mouse. The bone has all been resorbed. A second area in which biological colleagues are using our compounds is to study the mechanism of the anti-tumor effect of these drugs. So here is an experiment in an animal model, which is a breast cancer model. And they're going to compare the breast cancer mouse with the normal mouse on the right, the breast cancer mouse on the left. And what you're seeing is that they have injected the fluorescent drug, and as the fluorescent drug passes through the vasculature that supplies blood to the tumor, that was the red color you saw coming through the picture for a second, it leaks out into the tumor because the blood vessels that supply the tumor are very leaky. Whereas in the normal tissue, we don't even see the fluorescently labeled drug at all. So this proved that there is a mechanism whereby these drugs can leak out into a tumor after the patients received the dose. Then what are they doing in the tumor is the next question. So again, these are images from our collaborator, Dr. Rogers in Australia. And let's look at, in the interest of time, just this one. I guess we have to look at both of them. But what you're looking at here are tumor-associated macrophages in the tumor cell. And they're kind of like Pac-Man. They go through the cell and gobble up things that are of a certain size. And what the images showed, so we get this one to go, is that the green macrophage is gobbling up the red labeled bisphosphonate. Now you may ask, if you know some chemistry, how could something that's 10 micron in diameter, how can we see it gobbling up a molecule of the labeled drug? That's the key discovery from this image, which is that in the cancer cell there are these microparticles called microgranules. They may not be crystalline phosphate material, there may be a urea microgranule, but clearly they absorb the bisphosphonate that has been released in the tumor cell, and then the macrophage is ingesting the drug by ingesting these particles. And so the hypothesis is this is the mechanism by which these drugs exhibit their anti-tumor effect. So I think that's all the time I have left in my presentation, so I'll skip part 2. And simply thank you for your attention. We have maybe a minute or two for questions. Спасибо за внимание.
How do you know that with your rather large linker you don't change the specificity to the target of the drug?
So it's a fair question, but let me first say it isn't the linker which is large, but it's the dye which is large. The linker is only 3 or 4 atoms, but it's still a valid question. So we know that for 2 reasons. First of all, we can compare the bone affinity of the parent drug and of the labeled drug using special column techniques and to show that they correlate rather well. Secondly, respect to the biological activities I showed on the third to last slide, the labeled drug is still exhibiting the parent drug's effect as an anti-resorptive. So those are the data we have to answer your question, at least. Whether they convince you is up to you.
Charles, may I ask you, you suggested that the mechanism actually is the phagocytosis of the biphosphonate crystals, right? Of certain size.
You mean in the last slide?
Yes.
Yes.
And for phagocytosis, there is a certain demand for the size of these complexes. If they less than 1 micrometer, it will be another process. Does it matter which type of the process of your drug ingestion into the cell makes sense?
We can't answer this question because this is simply showing that there are particles of a size that are engulfed by the macrophage, which are absorbing a lot of the drug, in this case the fluorescent drug. It's already known that these drugs bind very well to microcrystalline phosphate salts, microcrystalline urea salts, presumably the same way. What is the effect on particle size and so forth? That remains to be studied. So That particular image we just published a month ago. Any other questions? No questions?
Yes,
No
a
questions
question.
in Russian?
Haven't you tried to add a dye in vivo? I mean, you ingest a drug with a small linker, for example, acetylene, and then you add a dye in vivo.
Ask the question in Russian, please.
Yeah. Вы пробовали вводить, непосредственно прикреплять краситель к молекуле лекарства уже в клетке, непосредственно в живой клетке?
Yes, we did. The dye is completely different from the dye linked to the drug. The dye has no bone affinity. The dye has no anti-resorptive activity. The dye doesn't co-concentrate in the animal model with the dye attached to the drug.
Возможно, вы не совсем поняли мой вопрос. Вам удобнее на русском или, если я скажу, на английском?
По-русски, конечно.
Просто если, как уже в первом вопросе сказали, молекула с прикрепленным красителем, это как-то может влиять на ее селективность, то можно сначала ввести просто молекулу с небольшим линкером, а потом уже попытаться присоединить к ней молекулу красителя уже в клетке, после того, как молекула лекарственного средства, она уже дойдет до, уже сконцентрируется в нужной локации в клетке.
So I think you're asking about what we call cargo drug.
Yes.
Deliveries. So this is something we're studying very actively. Other people are studying it. The idea is to attach some other drug, say a cancer drug, through the linker to the bisphosphonate. Use that to deliver it to the bone where you have the bone tumor. But then you have to come up with the right chemistry so that the cargo drug is released. And usually our focus is on putting a linker in, which is a substrate for an enzyme overexpressed in the tumor. So it's a great question.
Thanks.
Thank you.